This is another question from June 2018, paper 1, question number 23. This is a question on circle theorems as well as other calculations that involve a circle. Okay, so the first thing that you need to do, of course, if you come across anything like this, is to make sure you read and understand all the given information, because most of the times all the answers come from those statements. So in this case, you are told that points A, B, and C are on the circumference of the circle, and this circle is a center O. It's very key to mark this because you're going to use it as a reference somehow. We're also told that OB is 7 centimeters. So you can see from the circle that if O is the center, then definitely OB is the radius of the circle. And then angle AOB, that's the angle at the center, it's actually 60 degrees. Okay, and also you're told that in this question you're going to use pi is 22/7, right? So before you attempt to look at what the question is asking you to do, the first thing that you need to focus on is to try and fill in all the angles that you can possibly fill in. Remember, an angle is formed between two straight lines. Sometimes you find people, trying to fill in angles that are formed between an arc and a line. That does not exist. Okay, so as long as there is a curve in the straight line, there's no angle there. Angles only exist between straight lines. Okay, if you have an edge, let me say. Right, so in our case, you can always use that theorem which talks about the angle at the center and the angle at the circumference. So we know angle at the circumference is always half the angle at the center, or angle at the center is always twice the angle at the circumference. So in our case, you can see that C is at the circumference, and the angle at the center is 60 degrees. So automatically this angle is 30 degrees there. And then guys, this is a triangle. OAB is a triangle. And the fact that one of the angles is 60 degrees, it means all the angles in that probably triangle are all equal. Okay, so this will be definitely all right. So if this is an isosceles, all right. Okay, I think I was rushing things there. This is an isosceles triangle to start with. So if this is 60 degrees, right, we have two angles here, this angle here and this one there. So since this is an isosceles, why am I saying it's isosceles? Because a radius and a radius will obviously be the same. So a OOB is definitely equal to OA, and they're all 7 centimeters. That's why I'm saying that's an isosceles triangle, of course. So two angles of an isosceles triangle are always equal. Right, so if the top angle is 60 degrees, which means we are saying 180 minus 60 degrees, we are going to get 120 degrees. So the fact that those two angles are equal, it means we need to divide this 120 by 2, meaning to say each and one of those angles is 60 degrees as well. So this becomes 60 degrees, and that also is 60 degrees. Okay, that's what you probably, I think these are the only angles that you can fill in. Now let's go to the question. Part A wants you to find angle ACB. Looking at the diagram, you can see that ACB is actually the angle at the circumference, which is 30 degrees. And then B, you're finding OAB. OAB is the angle, this one, which is 60 degrees, right? So it's always key, it's ideal to first fill in the angles before you even look at what the question wants you to find, because if you try to read out what the question wants you to find and trace it on the diagram, you might end up getting confused. So the first thing that you need to do is to make sure that you try and fill in everything using the information that you be given. All right, now let's move on to part C, calculating the length of a minor arc. Okay, now we need to make sure that we get things straight, right? So this is what happens now if you have a circle and you've drawn some, what you call this, codes and stuff. All right, So looking at this diagram, I'm sure you can all realize or see that there's a chord AB there. So what it simply means is that this portion down here, okay, we can call it the minor segment, okay. Sorry about that, let me try to use a different ink. This is the minor segment. Minor segment. Segment is just a piece of a circle. So if you have a chord, we have a chord here. There's a chord here, right? This is a chord, and it's dividing our circle into two pieces. The bigger portion is the other side, okay. It's the other part of the circle. Let me just highlight so that maybe you can see what I'm talking about. Okay, this is what I'm talking about, this whole portion. Okay, I hope you can see. My color is not really clear. Let me use a different color, maybe red will do, right? This becomes the major segment. This one is the major segment, and the bottom part is the minor segment. Okay, I'm going to erase all these lines, all right, so that my diagram doesn't look very clumsy. Super. Okay, so the question wants us to find the length of the minor arc. So the minor, we have two arcs here. After dividing our shape into the major segment and the minor segment, we'll have two arcs. The major arc is the one which goes from here, runs from this point, right, from A all the way up to B there. This is the major arc. Major arc. And then the minor arc is down here, this line. This is the minor arc. Sorry, this is the minor arc. So where do we get these formulas from for calculating the major arc and the minor arc and so forth? What I will urge you to do when it comes to this one, you guys need to realize that you need to recall how to find the circumference of a circle. Let me say the perimeter of a circle in simple terms. For you to calculate the perimeter, you say it's 2 pi times the radius. That's how you calculate the perimeter of a circle, which is the circumference, of course. And also I want you to remember this formula, area of a circle. Area of a circle is pi r squared. These formulas are very key, especially when you're now dealing with a sector. All the formulas that we use for a sector, they emanate from these two guys. All right, so I'm going to explain everything now, how we can calculate the length of an arc. Okay, all right, let me just drag this a little bit down. Okay, so now if you're looking at that diagram, the area of the length of an arc, length of an arc. This is part C, is it? Length of an arc. What you can simply do, you can first write the formula of the whole circumference, right, which is 2 pi times the radius. And then now we are focusing on how much portion did we take from 360. You realize that the sector that we're dealing with was made from 60 degrees. Okay, so after writing this formula, you can then take the fraction from 360, which is 60 degrees over 360. You don't need to cram the formulas, guys. I know the formula for calculating the length of an arc, someone will say, is theta over 360 times 2 pi r. I know you guys maybe might be knowing this, but I want you not to cram or try to memorize all these formulas. You can simply focus on those two formulas that I just gave you, and then each time when you're dealing with a sector, you know that a sector is just a portion or a fraction of the whole circle, and the circle, a complete revolution is 360 degrees. So you are taking 60 degrees from 360. That's what you are doing. Then from here we can simplify everything, substitute everything that we have, right? We can try to cancel things out here. 0 cancels out 0 here. 6 into 6, 1. 6 into 3 into 36, that's 6 down there. We have 2 again here. 2 into 2, 1. 2 into 6, you get 3. Then let's substitute pi is 22 over 7 times the radius is, excuse me, it's 7 times 1 over 3. So this will give us, this cancels out, that cancels out. We're now left with 22 over 3. Then this will give us what? We can leave it as, since it's paper 1, we don't have a calculator, we can just leave it as a mixed number. Okay, so 3 into 22, that is 7, remainder 1 over 3. This will probably be the length of the arc. You try to change it into a decimal, it will give you 7.33333 recurring. So this is how you find the length of an arc, right? Then now let's move on to the area of a sector. The area of the sector. I hope you still remember that part D, you guys are supposed to calculate the area of the minor sector. Of course, we always have the minor and the major. The minor sector is this one down here. Let me just highlight it again. This is the minor sector, all this portion. This is the minor sector here. Just a second. Right, all this part, this is the minor sector. All this, that's the minor sector, and then the rest is the major sector. Okay, right, let me just remove those. Okay, so now we're going back again. What's the formula for calculating the area of a circle? The area of a circle is calculated using the formula pi r squared. So this is D, so it's the area of a sector. So you start with the formula for calculating the area, the whole area of the circle, and then you ask yourself, what fraction am I taking from the whole circle? That is 60 degrees over 360. So now we substitute our values. Of course, we can cancel out. I'm sure you noticed that this gives us, actually, if you try and divide this 16 to 61, and down there you have 6, right? Then we can substitute some other things. That's 22 over 7 times 7 squared times 1 over 6. So this will give us 22 over 7 times 49 times 1 over 6. And this will simplify to 7 into 7, 1, 7 there, 6 by 2, you get 3, by 2 there, you get 11. Up there we're getting 77 over 3. And when you divide 77 by 3, you get, as a mixed number, I think you're going to get 25 and 2 over 3. 25 and 2 over 3, which is around 25.666. To 3 significant figures, this gives us 25.7 centimeters squared now. Okay, so yeah, I hope we learned something from this. Unfortunately, it was a mixture of two things. It wasn't just circuit geometry. So if it was circuit geometry, it was going to be very easy. But it's good that we also touched on the sector of a circle.